So now we're going to look at our Part B questions. And the first question is an optimization question. And this is an application for physics. We have a raindrop with an initial mass of m naught that falls due to gravity while following the drop evaporates. So its mass is decreasing with time by the linear law. What this means is instead of the mass being constant, our mass is changing. It's evaporating as we go. Which means that with that evaporation, that evaporated water takes away some of the energy from the system. It's losing mass, it's losing energy. So we don't have this constant energy. So we can't connect potential and kinetic energy. So what we're going to do is we're just going to look at the kinetic energy. And we're going to first create an expression for kinetic energy, and then we're going to determine the maximum kinetic energy. So the first thing that we said is that a kinetic energy, as the kinetic energy of a falling body from rest is given by K of T, which equals mg squared T squared over 2, compute the kinetic energy of the raindrop. Substitute m equals m naught b minus bt. So this is simply saying K of T. Let me change this for a more contrasted color ink. This is saying that K of T equals m minus b of t times g squared t squared over 2, or K of T equals m g squared t squared, or sorry, m naught g squared t squared minus b g squared t cubed, and each of these are over 2 over 2. Now, one thing to note is that the kinetic energy can never be negative. So because the kinetic energy is never negative, this means that K of T must be greater than or equal to 0. Also, T must be greater than or equal to 0. So from here, we can determine what valid T values we have for this expression are. And to do this, we can create a cheeky little sign chart about the roots. We have 0, and we have the roots m naught over b. And if we look at our factors, m naught minus bt and g squared t squared over 2, this m naught minus bt is negative and then positive, changing at m naught over b. And this entire term here is positive everywhere, giving us positive, negative, positive. However, we can't have a negative time. These are 0 values. So our t, or our domain, is the interval 0 to m naught over b. And this will be important for our next part B, where we're going to determine at what time does the raindrop have the largest. And here it's going to be kinetic energy. Instead of potential energy, it's going to be kinetic energy. This is asking what is the max of KT equals what? To compute this, first what we're going to do, we note that this is a closed interval and that our function's continuous. So as KT is continuous over a closed interval, we can use the absolute extrema over a closed interval test. What this is one, find critical points and compute the corresponding critical value, and two, compare the critical value with the value of the function at the endpoints. So first we need to figure out what our critical points are. And to do this, we take the derivative of k with respect to t, and this equals m naught g squared t minus 3 over 2 g squared t squared, which equals 2m naught minus 3t all times g squared t over 2. K prime of t equals 0 when t equals 0 or t equals 2m naught over 3. Oh, this is a b. I'm missing a b. There should be a b here. So there's a b here, or 2/3 m over b. Right? Also, the derivative is defined for all t. Thus, now we check to see if these locations where the derivative equals zeros are critical points or not. And to check if they're critical points, we check if they're within the domain. As t equals 0 is on the boundary of the domain, it is not a critical point. As 2 over 3 m naught over b is within the domain, it is a critical point. Right? So we have a critical point at 2/3 m naught over b. And the absolute value of our closed interval test tells us to check the critical values, which is plugging in the critical point to our function, with the endpoint. So k of 0 equals 0. K of 2/3 m naught over b equals, plugging it into my original function, scroll up a little bit, is going to be 1/3 m naught times g squared 2 over 3 m naught over b squared all over 2, which is greater than 0, and k of m naught over b equals 0. Thus, the maximum potential, kinetic energy occurs when T equals m naught, or 2/3 m naught over b.